Welcome back to Physics 141 Online. We've spent quite a bit of time talking about motion in one dimension, and that's going to pay off because when we start to tackle motion in 2 or 3 dimensions, the mathematics is quite similar to what we did in one-dimensional motion. Before I launch out into the beginning of Chapter 3, where we begin to learn the mathematical techniques for describing 2 and 3-dimensional motion, let me just remind you of a little quote that was in my freshman physics book. Inside the book, the author reminded us that problems worthy of attack prove their worth by hitting back. And so you may have encountered that as you have been working on the first couple of homework assignments, and if you did, that's okay, because some of the problems are warm-up problems. They're kind of easy, but then we quickly graduate into more challenging problems that are really worthy of your best efforts. And then the basic punchline here is that just like in any area of sports or athletic endeavor, learning physics involves resistance training. We're going to stretch and bend and twist our minds, and as we do that, we're going to get better at it. And then here's just a little humorous thing I found from an old Nike ad. Even NFL players need to brush up on physics. Here's Michael Vick, who many of you recognize from his quarterback exploits in the NFL, reading a book, Quantum Physics in Short Yardage Situations. I'm not sure that's going to help him very much, but it is humorous. So here's where we're going in the second section of the course that deals with 2-dimensional and 3-dimensional motion. And this is, of course, the topics from Chapter 3 in our textbooks. We will start to go through these different sections and lead up to a mathematical ability to quantitatively analyze projectile motion, which is the kind of motion that an object encounters when it's thrown into the air near the Earth's surface. And first, we have to become familiar with the language and properties of vectors. In one-dimensional motion, usually we don't think about vectors because the object is simply confined to move along either the positive or negative x direction. And of course, the sign indicates which direction the motion is taking place in, but it's just a single direction. However, once we introduce the freedom for that object to move in more than one dimension, 2 or 3 dimensions is usually common, then we have to worry about the direction, not only the speed, for example, but the direction of motion. And so a vector is a mathematical quantity that represents something physical that has both magnitude and direction. And so if I was driving a car and going at a certain velocity v, that velocity would be specified in the strict way that a vector is by giving its magnitude, let's say 30 miles an hour, and its direction, which might be northeast. And both of those are required to specify the vector. On the other hand, there are plenty of quantities in nature that have magnitude but no direction. Those are called scalars. For example, the temperature of the room. That's got a magnitude, but it doesn't have a direction. The mass, my mass, has a magnitude, but it doesn't have a direction because I'm not normally moving. So that mass is not a quantity that involves any kind of direction. As I gave those examples, there you go. Vector quantities, on the other hand, are the ones that, especially in mechanics, we are usually interested in. Velocity, acceleration, displacement, force, momentum, all of these things have direction as well as magnitude. So there's a couple of different ways to describe a vector, and we actually are going to use 2 of them quite commonly. One of them is more for the purposes of an illustration, and the second one is more for the purposes of quantitative analysis, actually figuring something out mathematically. So graphically, we write down a vector as an arrow. And we always write down a label for that vector with a half arrow on top of it. It's very important to do that because without that half arrow, then we're just talking about a symbol for the magnitude of a quantity. With the half arrow, we see that this A has not only length or magnitude, but it's got direction. The direction's obvious from the scale of the sketch, but the length of the arrow is proportional to the magnitude of the vector. Now this is not to imply that all vectors are length vectors. We could have a velocity vector. And of course, a velocity has something that's in a magnitude that's in meters per second. It doesn't just have a length. But we still draw a velocity vector as an arrow, and we just draw it so that the size, the magnitude of it, is proportional to its length on the sketch. Analytically, and this is the second method of describing vectors, we might take this vector A and introduce a coordinate system. And when we introduce a coordinate system, we can see that that specifies in a very clear way the direction and the magnitude of A, because the coordinate system, then we could define the angle theta that A makes with the x-axis. And we also would realize that A could be specified by what we call its components. A sub x is that portion of A that lies along the x-axis. A sub y is that portion of A that lies along the y-axis. So, for example, starting at the origin, where the tip of A is located, where the tail of A is located, we would move along the x-axis by an amount equal to ax, and then turn and move along the y-axis by an amount equal to a sub y, and that would take us from the tail of A to the head of A. And mathematically, we write down exactly that kind of statement, like this, that we say the vector A is equal to the sum of two pieces. That would be A sub x along the x direction plus A sub y along the y direction. And we use a special kind of notation to do this. We use these vectors, special vectors, I hat and j hat. And I hat and j hat are called unit vectors. They are vectors that have length equal to 1, and they lie along the coordinate axes. In fact, if we had a z-axis, if we had a vector that had component in the z direction, we would have I hat, j hat, and then we would also have another term that would have k hat. So I and j, which we usually describe as I hat and j hat, they represent these vectors along the coordinate directions that have length equal to 1. So in this equation, A equals ax I hat, it means that A is composed, first of all, starting from the origin, by moving in the I hat direction, moving in the x direction by an amount ax, and then turning and moving in the y direction by an amount ay times this unit vector j hat. Trigonometrically, right, if we wanted to find out the values of those components, we can do that very easily using the sine and cosine of theta. For example, the sine of theta is the opposite side, which is a sub y, over the hypotenuse of A. Solving for a sub y gives us ay equals a sine of theta. And similarly, the equation here on the left is obtained if we realize that the cosine of theta is ax over A. So that's all the trigonometry review I'm going to do. Most of this should be familiar to you from previous courses. Again, ax and ay are called the x and y components of the vector A. Now, what do we do with vectors? Often we will have an occasion to either add or subtract them. Later on in the course, we'll also talk about special ways of multiplying vectors. But for now, let's just worry about addition and subtraction. The graphical method is the so-called head-to-tail method. It's not used if we want to generate strictly quantitative results, but it's nice to show as an illustration of what the calculations are actually doing. So the so-called head-to-tail method is how we add two vectors. We take a vector A, and we take the tail of B and put it at the head of A. So A, let's say, is a displacement in the direction indicated by the arrow. B is a displacement in this direction, and then A plus B is obtained by starting from the tail of the first vector and going all the way to the head of the second vector. So it's head-to-tail addition. And that means it's A plus B. It's the resultant vector when vector A and vector B are added together. It's very easy to see how this makes sense in terms of a displacement. If we move along vector A from the tail to the head, and then we turn and move along vector B to here, the net displacement is given by the vector A plus B. What about subtraction? Well, subtraction is nothing more than adding the opposite of a vector. So here's a and b. We're going to use the same vectors a and b again, only I want to actually subtract b from a. So I want to form a minus b. So here the dotted line indicates b, and if we just flip that over backwards, we get negative b. It's doing the same thing but in the opposite direction. So a plus negative b, if we orient them head to tail as before, gives me a plus negative b or a minus b. So hopefully that is helpful. Often we'll draw sketches like this even when we're going to go on and use our trigonometry knowledge to calculate the actual components of the vector a plus b or a minus b. But sometimes it's helpful to draw a sketch. Now, graphically, of course, we get an approximate result. We can at least see that the vector a plus b has a positive x component and a positive y component. But what about the numbers? If we wanted to add the two vectors quantitatively, we would realize that a, the vector a, is ax I hat plus ay j hat. And the vector b is bx I hat plus by j hat. So if we just substitute for both of those and simplify, we'll see that there are two terms in the I hat direction, and then there are two terms in the j hat direction. And it's as simple as that. If I know the components of a and b along x and along y, I just add them up and I get my answer. So, what good is all this? Well, our interest ultimately is in studying motion. Motion requires a treatment of position, velocity, acceleration, all that stuff. So let's just go through how this is done. And I will do this in the full general case of three-dimensional motion. So the position vector that indicates a position in space, a point in space, from the origin, let's say, is indicated by r. And r has components along I, j, and k, along the x-axis, the y-axis, and the z-axis. So the vector r takes me from the origin to a point at position x, y, z. It means I move along the x-axis, indicated by I hat, by an amount x, then I move along the y-axis by an amount y, and along the z-axis by an amount z, taking me to a final point that has coordinates x, y, z. It's that easy. Okay? The general velocity vector, well, velocity represents the time derivative of the position. When we wrote this in one-dimensional motion, we just called this v, and we said this was dx over dt. But now v is a vector, so we're going to write this derivative, the velocity, as a vector itself. But the only thing is, when we form the derivative dr dt, we're just going to differentiate each of the vector components of r with respect to time. So if I took this literally, right, I would differentiate, I would have dx dt I hat plus dy dt j hat plus dz dt k hat. And that's correct, but we'll just realize that each term can be written more simply as a component of the velocity vector. dx dt is the change in x with respect to t, and that's the velocity along the x direction. So we will call that vx. And in the same way, dy dt is vy, and dz over dt is equal to vz. So that's the general expression for a velocity vector where, as I said, these individual components of the velocity vector are nothing more than the derivatives of x with respect to t, y with respect to t, and z with respect to t. The acceleration vector can be written down much the same way. The acceleration in general is dv dt with vector signs on both acceleration and velocity. Any general vector a is going to be written down as ax I hat plus ay j hat plus az k hat. But now there's a relationship between the acceleration components a and the velocity v. So ax is dvx dt, ay is dvy dt, az is dvz dt. Each of these components, the vx, the vy, and the vz components, can all have their own kind of time dependence. And so you could have an acceleration vector with very different components. So that's basically, go back there, that's basically all there is to it. Except now we will put these vectors into service in doing some simple calculations for two-dimensional and three-dimensional motion with constant acceleration. All right. ultimately we're going toward projectile motion where that constant acceleration will be negative g in the y direction. But for now, let's just do the general case. So for 1D motion with constant acceleration, remember we had these kinematic equations. And one of them was v minus v0 is at. But now for the case of 2 or 3-dimensional motion, we want to use the same equation, but use it, of course, with vector signs. Because the basic principle is still the same, but we have to take into account that v and v0 and a now have directions, and they're not necessarily oriented along the x direction. So the equation in the box is the new version of the equation. And in 2 dimensions, what that means is if I take v and I write it as vx I hat plus vy j hat, that's the most general way of writing a vector v. And now we subtract off the same kind of quantity, but we're going to add a 0 to the subscript so that the x component of the initial velocity is vx0. The y component would be vy0. And finally, the right-hand side would just have the general vector a times t. So ax I hat plus ay j hat times t. This equation looks a little bit more complicated, but I hope you realize that it actually just comes from the original equation that we figured out for 1-dimensional motion. So in any vector equation, the components must be equal to each other. In other words, if there are components of x and y on one side of the equation, then the components of x and y on the other side of the equation have to be equal to the ones on the left. Right? What do we mean by that? We look at this and we say, oh, on the left-hand side there are 2 terms that represent velocities in the x direction, vx I hat and vx0 I hat. On the right-hand side there's only 1 term, but because of the way that vectors add, right, if we have a sum of vectors and that's equal to another sum of vectors, the individual components have to equal each other on the different sides of the equal sign. So what this amounts to is we take vx, we take vx0, and we take axt and just realize that they have to be equal in this fashion. So vx minus vx0 is axt. And the same kind of thing holds true if we identify the other 3 terms. We realize that they all have to be equal, and that will allow us to write down vy minus vy0 equals ayt. So these 2 equations are very simple ones, and they're very, very similar to what we did in 1 dimension. The only difference in 1 dimension was there was no x and there was no y. Similarly, for the displacement kinematic equation, which is the delta x equation, right? X minus x0 is vx0t plus 1/2 axt squared, and the same thing for the displacement in the y direction. The only difference, that this equation looks just like the 1-dimensional motion equation, except we put subscripts on x, on v, and on a in order to indicate which ones represent initial quantities and along which direction they are pointing. So we've now taken the first kinematic equation and we've got a form for the x-axis and a form for the y-axis. Then the same thing holds true for the second kinematic equation. And one more thing that we can do, by combining these 2, we can get equations that look very similar to what we had once again for 1-dimensional motion. And we could continue this way, right, etc. We could do the other 2 equations, but I'm not going to take the trouble here because generally speaking, these 3 equations are the ones we use most often. So 2-dimensional motion is really no more complicated than 1-dimensional motion, except we have twice as many equations that we can use. Here's an example. Okay, what I want to do is illustrate principles of vector addition, but I also want to make use of these kinematic equations for a simple case of 2-dimensional motion. An object is at the origin at time 0 with an initial velocity given by this, v0. It moves with constant acceleration, and a short time later we somehow measure its velocity again at t equals 3 seconds, and we find its velocity to be the following: 9i plus 7j meters per second. So we want to find 2 things: the object's acceleration vector and an expression for the object's position vector at any time, which seems like it might be a lot of work, but it's actually not too bad. The way that we can tell the object is accelerating, of course, is its velocity vector is changing. the components for I and j are different after 3 seconds than they were initially. So let's use our knowledge of vector addition and our simple knowledge of kinematic equations to solve this problem. Okay, here is my example problem rewritten on my stylus so I can solve it for you. And I've just written down what the initial vector was at time 0. So we call this vector v0. It was 3i hat minus 2j hat in meters per second. We were told at time t equals 3 seconds. Here's what it is now. Also, I didn't put the units down here, but it's still also in meters per second. So I'll put that down. And we were told that the object is at x equals 0 at t equals 0. It was at the origin, x equals 0, and of course y0 equals 0 at t equals 0. So find a and find the position. Well, a is not too bad to do, because we know, of course, that in order to find the vector a, we need its components. We need ax and we need ay, and if we can find them, then all we have to do is write them into this equation here and say we're done, right? Because we would know ax, we would know ay, and that's all there is to know about the vector a. So ax and ay we need to find. What do we know? We know vx0 and we know vx. Those are the x components of the two given vectors, right? So we can realize that from the general kinematic equation, v equals v0 plus at, right, we know that that actually means that there are two individual equations, one for vx and ax, and another for vy and for ay. Alright, so what we need to do is solve for ax and ay using these two equations. So let me just do that and then we'll plug the numbers in. I'm going to do a little bit of quickie algebra here. So if I take the vx0, subtract it from both sides, I will get axt equals vx minus vx0. So ax is equal to vx minus vx0 over t. And likewise, if I solve for ay, I'll get exactly the same thing. I'll have an equation that will say ay is equal to vy minus v0y over t. All right, so to find those two components of acceleration, I just need to plug in the values. So I'll do it over here. Ax then equals, in the numerator, vx is the x component of the final velocity vector. That would be 9, right, meters per second, minus vx0, which is the x component of the v0 vector. That would be 3 meters per second. The time, of course, is 3 seconds. So what do we have here? We've got 1. No, actually, we've got 2, don't we? 9 minus 3 is 6. So 6 over 3 is 2. So we've got 2 meters per second squared. And I know that because the unit in the numerator is meters per second and then seconds in the denominator. So we've got that. A sub y, likewise, can be found very easily. A sub y will also be this kind of a fraction. Vy is 7 meters per second. Vy0 is negative 2. So it's minus, be careful here, minus negative 2 meters per second. Right, divided by 3 seconds again. And so what do we get? We have, again, 9 meters per second over 3 meters per second. So this is just, or over 3 seconds. So this is just 3 meters per second squared. So we've got ax, we've got ay. Now, finally, a, which is what we asked for. We were asked for the acceleration vector. A is equal to ax I hat. So it's 2 meters per second squared I hat plus 3 meters per second squared j hat. And we're done. That's all there is to do. That's called writing down A in unit vector notation. And if I really wanted to, I could calculate the magnitude of A, and then I could calculate the angle it makes with the x-axis, but I don't need to. I'm done with what I was asked to do. Now to find the position at any time, all right, now we want to find the vector r, right? R is our position vector, and it would be x I hat plus y j hat. So can we find an expression for x and for y from the given information? Sure enough, we know the kinematic equations. X minus x0 equals vx0t plus a half ax t squared. We know that. And we also know y minus y0 is vy0t plus a half ay t squared. And we are trying to solve for x and for y. If we can solve for them and plug them into the expression for the position vector, we're done. Now it says at any time, so we don't just want to find the position at a specific time like 3 seconds. We want to find an expression for the position at any time. So our answer will include just t as a variable. But let's look at these two equations. First of all, we see they simplify because the object was at the origin at time t equals 0. So these two both go away, and we're left with what's on the right-hand side. So x, now I'll plug in the numbers I have. X is vx0t. Vx0 is right over here. That's 3 meters per second. So it's 3 meters per second t. That gives me the first term, plus a half ax t squared. Ax is 2. Right? Half times 2 is 1. So plus 1 meter per second times, ax is meter per second squared. So it's meter per second squared times t squared. And that's great because that gives me x at any time t. All I did was take the first equation and substitute in the values of vx0 and ax. Likewise, for y, I will get vy0 times t. Vy0 is negative 2, so I'll get negative 2 meters per second times t, plus a half ay. So a half ay is equal to 3 meters per second squared. Half of that is 3 halves, so 3 halves meters per second squared times t squared. All right, and that pretty much gives us what we need. Note that the units, if we actually were to plug in a value for t in all of these terms, if I plugged in t here in seconds, the seconds would cancel and I'd be left with a distance in meters, as I should. The same thing would be true for the second term. So r is equal to now x times I hat plus y times j hat. And this is just a little tedious, but it does give us the final answer. 3 meters per second t plus 1 meter per second squared t squared times I hat then I have to now put in my j hat term, which is going to be y times j hat. So this is plus negative 2 meters per second t plus 3 halves meters per second squared t squared times j hat. And that's it. It looks kind of messy, but it gives me all the information there is to know about this object. It tells me, give me a time t, say t equals 5 seconds. I can tell you where the object is at any time because this will give me its x-coordinate. The first term will be the x-coordinate. The second term will be the y-coordinate. And that'll tell me where it is as it moves through space. So that is the solution to this problem. It shows how we use the kinematic equations, basically the same equations that we used in one dimension, but we now just have one of those equations for each of the coordinate directions. And it also reviews how we do vector addition and solving for vector components. So you'll have occasion to use this kind of approach to lots of the homework problems, and I'll see you in class.